Some functions are the products of other simpler functions. For example, the function h of x equals x times e to the x is the product of the function f of x equals x and g of x equals e to the x. In such a situation, it would be useful if there was a rule that established how the derivative of the product is related to the derivatives of each of the factors. Fortunately, there is, and it's the so-called product rule. Succinctly, the product rule says that if h of x is the function which is the product of f of x and g of x, then the derivative of h of x is given by f prime of x times g of x plus f of x times g prime of x. One way of thinking about the expression on the right-hand side is that it's the one you would get from the product f times g by applying the prime to each factor separately, and then summing those terms together. Indeed, the first term is the one where you apply the prime to f, and the second term is the one where you apply the prime to g. Equipped with this rule, then, we can compute the derivative of the product x times e to the x. In this situation, our function f is f of x equals x, and g is g of x equals e to the x. We also know the derivatives of these functions as f prime of x equals 1 and g prime of x equals e to the x. Using our product rule, then, we can compute the derivative of h. According to the rule, we should write f prime times g plus f times g prime. Using our computations we did, we find that this is equal to 1 times e to the x plus e to the x times x. Although this is certainly an acceptable expression for the derivative of h, it's also possible to factor out the e to the x term if you'd like, in order to obtain an expression of e to the x times 1 plus x. Now, there's another rule too called quotient rule, which deals with situations where a function is the quotient of two other functions. Specifically, if h is the quotient of f and g, then the derivative of h is given by g of x times f prime of x minus f of x times g prime of x all over g of x squared. At first glance, this rule appears a little bit more complicated than the product rule, but thankfully there's a helpful mnemonic to remember it. One particularly helpful mnemonic is a rhyme, and it says that the derivative is equal to low d high minus high d low, draw the line and square below. Here, low means the denominator and high means the numerator. The term d denotes the first letter of derivative, to suggest that you should take the derivative of the expression that follows. Let's see how we can use this quotient rule through an example. Suppose that h is the function h of x equals 3x plus 1 over x squared plus 2. To find the derivative, we'll use the quotient rule. Let's write f of x for the numerator and g of x for the denominator. Then we can compute the derivatives too. F prime is just 3 and g prime is just 2x. Applying the quotient rule, then, we find that the derivative of h is equal to low d high, where low is x squared plus 2 and d high is 3, minus high d low, where high is 3x plus 1 and d low is 2x. Draw the line and square below. Of course, we could expand the numerator to put the fraction in another form, even though it's not entirely necessary to do so. As a final example, we'll mention that it's possible to use the product rule and quotient rule in conjunction with one another. For example, suppose that h of x is the function 4x squared e to the x all over x plus 1. Because h is a quotient, we'll use the quotient rule, but in doing so, because the numerator is itself a product, we realize that we'll have to use the product rule too. Let's first write out what the quotient rule says. With the help of our mnemonic, we write low d high minus high d low, draw the line, and square below. Now, let's take a look at the derivative of 4x squared e to the x. This derivative can be found using the product rule, which says that we should apply d dx to each term in the product separately and then add those terms together. What we get when we do so is 8x e to the x plus 4x squared e to the x. The other derivative in the numerator is much easier. It's just the derivative of x plus 1, which is 1. Making these substitutions then, we find the total derivative. Of course, as usual, it's always possible to expand the numerator in the fraction to make it look a little bit nicer, but of course, it's not entirely necessary to do so.